Okay, I have 10 after here, and suppose it's probably good for us to continue, and we can do that by having a look here at exercise number 5. So this is, oh, it's still private. Oops. Yeah, our exercise is about viscous flow of ice. So you can see from the title there. And it's a couple things to note. One is that the exercise is due by 8:15 next week on Tuesday. So the 6th is Independence Day. That's a holiday, of course. And so we won't have class at our regularly scheduled time on next week on Tuesday instead. So instead of our Monday afternoon lovely time at 2:15, we'll be at 8:15 Tuesday morning, the 7th of December. So hopefully you don't have a raucous Independence Day celebration. I suppose that would be quite unusual, but yeah, be aware. So the due date is moved to be at the start of class next time, which will be Tuesday at 8:15. Otherwise, I think this is pretty standard landing page for the exercise, but let's have a look at what the exercise itself is all about. So yeah, we'll look at ice flow as a viscous fluid. First, looking at ice flowing in an open channel. And in this case, what this means is like we have a map view looking down on a glacier flowing between two valley walls. And as usual, we'll start out by having you copy your script file from exercise number 4, your intro QG functions script file you can copy. And then you run this first test cell just to make sure your functions from the previous week are working properly. That's a good thing for us to know before we get started, that the functions you have from the last time are working okay. Once you've done that, you can go into part 1, which is essentially just to take a look at that background and theory document that I already have shown you before we took the break. So you can go there, have a look. This link should hopefully open that up. Yes, it does. So you can go and have a look at the background and theory for problem number 1 and problem number 2 actually as well. There you'll find eventually that you end up with this kind of velocity equation that looks like this. So this is equation 10 just taken out of the theory section itself. Things don't format so nicely here in GitHub for the inline equations, but you'll see if you look at the notebook in Jupyter Lab that everything should look nice with a description of these different terms that are here. Your first job is to create a function, a pressure gradient function, to calculate this term here in the middle, P1 minus P0 over L to the power n. So you can rearrange this equation in order to solve for this term. And when you solve for that term, you're going to be given a velocity that you can use here for your u that you can plug in there. You're going to be given a value of h and a value of y, and that will allow you then to solve for what the P1 minus P0 over L to the power n term would be equal to. The reason is we don't know the pressure gradient, but we do have other things we can observe about our ice in this example, like how wide is the glacier from one wall to the other, and what are the sort of distances that we're dealing with? What is the kind of property that we want to use here? A is our viscosity constant. So what do we want to use for the viscosity constant? Well, you're given a number for that, and then you're asked to come up with a function to calculate this pressure gradient term, essentially. So your function will have a few terms in it. It'll have exponent, which of course is the power law exponent n for the viscous flow. The width, which would be our h, I think, in the equation that's given here. Viscosity constant is a, and the velocity max is going to be something that you're given here. I think that's our velocity max given in meters per second there. So you'll make a function in your script file, and then there's some tests to see if your function's working properly. After that, we can then come up with an ice flow velocity function. So now, in the first part, you're calculating just to figure out what is this P1 minus P0 over L term. Once you know that, for whatever n value you have, you'll be able to then plug in that term to this equation to calculate what the velocity is. So you'll create another function here for calculating the velocity of the ice from one wall to the other of this channel. Again, it'll have a lot of the same parameters that you pass into it: exponent, width, viscosity constant, and velocity max, in addition to a channel width array y. So this would be like a NumPy array that goes from one wall of the channel to the other with the specified distance of the points between them. So you'll make your function again. Your function that you create, called channel velocity, should use the channel pressure function that you created in part 2. So that's what you'll have to think about a little bit, is that you're going to want to call your channel pressure function in your channel velocity function in order to calculate what the velocity of the ice is in the channel. So that's the challenge in this case. But again, you have some tests to see whether you're on the right track. Then, once you've got your two functions working, you can actually go about calculating the velocities that you want to calculate for your glacier geometry that you have, and you're given some properties to use for that. So you'll calculate this for different power law exponents, 2, 3, 4, and 5, just to look at how the velocity pattern varies in those different examples. And then you'll have calculated, I think in this case, you'll put them into a pandas data frame, but you'll calculate those different velocities and store them as separate columns in your pandas data frame. Finally, then you'll make a plot for your different velocities so you can see how they compare to one another. And you'll, of course, write a little caption as well. So that's part 1, or problem 1, rather. Problem number 2 is to compare our velocities to observations from the Saskatchewan Glacier, and this is in western Canada in Alberta, so near the Banff National Park, which if you haven't Googled Banff National Park to have a look, you should do that. There's some really beautiful scenery there, wonderfully kind of bright blue lakes filled with very fine glacial sediment and things like that are really spectacular looking. Very nice landscape in general. So we have our model where we can calculate velocities, and now we have observations of velocities from the Saskatchewan Glacier, and we're going to compare the two. That's the whole point here in problem number 2. So you've got a data file you can read in that has velocity measurements in it. So these are at different distances from the center of the glacial channel. You can see different velocities in meters per year and meters per second. And that's what's in the data file, so you'll read that in first. Then step 2 is to compare the predicted velocities you have from problem number 1 to these observed velocities, and we're going to use the chi-squared function from way back in exercise 2 to quantify how well our observations fit the observed velocity pattern. So you're going to have a basically relatively straightforward task in that sense, that you'll have observed velocities, you'll have velocities where you've calculated the ice flow velocity, and then you'll compare the two. One thing you'll notice is that we don't have a standard deviation for our measurements of the ice velocity. You see here, it's just the velocity, there's no standard deviation. So you're asked then, or well, you're basically given a standard deviation array where we just say, arbitrarily, let's assume it's 2 meters per year for the standard deviation, just to give some number that's needed to use the chi-squared function. So chi-squared function expects an observed velocity, a predicted velocity from our model, and then some standard deviation in the observed velocity. And we'll just put in some constant value there just to be able to use that chi-squared function. And again, what you'll do after you've done that is you'll plot your velocity profiles that you've calculated earlier, as well as the measurement from different points across the Saskatchewan Glacier, and then you'll add some axis labels and a caption and things like that. And you're pretty much done then with problem number 2. For problem number 3, it is optional. So this was previously part of the exercise. I made the decision to make it optional this time just because I think it is quite time consuming to basically repeat this whole same process for a different equation. But if you want to sort of have the experience, if you want a little bit of extra practice, you can basically do the same thing it's done in problems 1 and 2, again in problem 3, but now looking for a velocity of ice flowing down an inclined plane. And again, you're given a link first to the background and theory, so you can read through that. Then you've got a velocity function here, where you're asked to first come up with a gravitational force function, because we don't know this term gamma x that relates to the gravitational force. And so you have to find a function to solve for this gamma x to then be able to calculate what that gamma x value would be for different power law exponents. So you make that function, very similar to problem number 1. Then you make a velocity flow function, again, similar to problem number 1. Read in some ice velocities. In this case, we're going from 0 depth up to 209 meters above the bedrock, and there's the velocity profile that's then able to be plotted here. You'll compare the observed ice flow velocities to your predictions once again, and finally then plot up your results. And at the very end, if you'd like, there are a few optional reflection questions where you can look back at what you calculated and think a little bit more about things like, what's the most likely power law exponent for glacial ice based on your calculations, and how sensitive is the velocity of the ice to the power law exponent. So that's exercise number 5. And it doesn't quite nicely fit into the theme of thermochronology so closely, but it's I think I like the kind of ideas in the exercise, in the sense that you get to do some rearranging of equations, you get to practice making some functions more, and then next week when we come back to our thermochronology theme, we can work on building our own numerical model where we start combining these different functions you've been working on for the past several weeks to create a single coherent numerical model that uses many of those functions. Are there any questions at this point? I'm not seeing anything in chat or any hands up in the Zoom participant list. So if that's the case, then maybe what I will do is I'll stop the recording, and I'll stop my screen share, and let you go ahead and get started having a look at the exercise. And if there are questions that come up once you've had a look through the exercise, you can maybe feel free to let me know. I'll stick around until the normal ending time, right around 4 o'clock, as long as anyone is here. I can stick around. You don't have to if you don't want to, but if you'd like to have a look at the exercise and have the opportunity to ask some questions, you're welcome to do so between now and 4 o'clock. So otherwise, I think Friday we'll still have our normal exercise session. Levi is gone this week, so I will be filling in for him in the exercise session on Friday. And I think we'll be able to kind of do things normally there. And if there's any interest, it may also be possible for us to have a question and answer session on Zoom on Wednesday or Thursday if there's interest. So far, I think we've had 2 of them, and I don't know that anyone has shown up yet. So if there's interest, let me know, and we can try to be on Zoom, or I can at least be on Zoom to answer questions on either Thursday or Wednesday afternoon. Actually, maybe, I think either one of those times. Okay, so yeah, I'm going to stop sharing now and stop the recording, and I'll be here if you have any questions. Otherwise, see you Friday in the exercise session.